So what we're finding is that a lot of the slowness of implementing OR solutions and a lot of the reasons that people don't implement OR solutions is that the iterations just take too much time because you're going back and forth between people of different expertise, and finding time on the calendar every iteration takes weeks, and so the whole process gets massively delayed. And it's not because of the time required to solve each particular part of it, it's because of the time to go through this flywheel over and over again.
You kind of went into this thinking that the math was going to be the bottleneck, and that wasn't none of the subjects sort of identified that as the bottleneck. What did they flag? What were some consistent patterns around where the problems lived? Madeline, I think you earlier mentioned the cycle time and the iteration time. What other things popped up? Hello, and welcome to another edition of the Decision Intelligence Lab podcast. Along with my co-host, Michael Watson, I'm thrilled to introduce our two guests today, Connor Lawless and Madeleine Udell, both at Stanford's Management Science and Engineering Department at the moment, my alma mater. Very pleased to have them on. Connor's the lead author on a paper that we're going to talk about today called It Was a Magical Box, Understanding Practitioner Workflows and Needs in Optimization. And Madeleine is an optimization specialist who worked on this paper, and I was really thrilled to get her perspective as a researcher on these implementation challenges. Just a little bit about our guests before I throw it over to Mike. Madeleine is on the faculty in the Management Science and Engineering Department at Stanford, and her work is at the intersection of optimization, machine learning, and decision-making. She's also the co-author of convex.jl, which is a convex optimization package in Julia, as well as a long list of papers on real-world decision problems. And Connor is just finishing up his postdoctoral research work at Stanford and will be joining a startup called Percepta that's building LLM-powered tools for optimization modeling. He's got a PhD in integer programming and is also really interested in human computer interface related issues. So we've got a terrific couple of guests. We're happy to have them. Mike, over to you to get us started.
All right, welcome to the podcast. I'll just kick it off and ask, what prompted you to write this paper? What were you trying to uncover?
Awesome. Well, thanks for having us. Yeah, so I think what kind of prompted at least my interest in this paper was I spent the last kind of couple years looking at building LM tools to help non-expert users model optimization problems. And at some point, we kind of took a step back and asked ourselves, is this really the bottleneck practitioners are facing, going from a text description to a concrete model, or are there kind of better tools that we can be building? And I think this connects to kind of a more kind of existential problem we've been having in the field of OR, which is that in general, OR is this pretty inaccessible toolkit, right? If we compare it to something like machine learning, we can teach undergrads how to spin up a neural network model in 3 lines of code these days. And yet there's still this kind of perception that OR is something that can really only be practiced by folks with PhDs. So our kind of goal going into this paper was to understand, okay, so if we say this is something that only PhDs can do, what exactly are they doing? What are the opportunities to make this more accessible? And, in general, make OR more accessible and have broader reach of all these tools that we're building.
Excellent. Just to kind of dig into that, the paper talks about the process of building an optimization model as having 6 stages, starting with kind of problem elicitation, ending with deployment. Can you talk us through those stages? And then the follow-up that kind of tagged with that is, where does iteration fit, or is there iteration at every step along the way in what you found?
Yeah, so at a high level, kind of the process folks follow is first, to set the stage a little bit, typically the people that we interviewed were optimization model developers. So these are folks typically with an OR background whose goal was to come up with these optimization models. And very rarely those folks are the experts in the domain in which they're applying these tools, right? You might be someone who has a PhD from Northwestern who's going off to help some mining engineers maximize throughput of iron ore smelting, right? Nothing about iron ore smelting. So typically how it starts is there's this really long problem elicitation phase where that OR expert has to sit down with the mining engineer, understand what iron ore is, how does it go through the process, all of those details. This is typically a super, super slow process because, there's a lot of expertise that goes into iron ore smelting that you need to kind of extract. Once you have that, you also have to get the associated data, right? Optimization problems run on data, whether that be constraints relating to how much iron ore you can get through the system, what are the demand distributions, all of that. So that takes a lot of work too. And once you have those kind of an understanding of the decision-making problem and the data needed into it, you can then go constructing your OR model. So we call this model development. This is typically what we teach in undergrad courses or even grad school courses, right? How do we go to a concrete myth model where we can write down all of our decision variables and constraints? Once you have that, you can go about implementing it. This is typically a super pragmatic process, right? There's trade-offs between how faithful we're implementing that model versus heuristics and all these kind of computational considerations. Then you need to validate that model. So even after you've done all this hard work of building a myth model, coding it up, being able to solve it quick enough, you still have to go back to those original mining engineers and convince them that you're actually solving the problem. And this is, again, one of those like really, really big bottlenecks because those mining engineers don't necessarily know the math. So you have to figure out, how am I going to prove to these mining engineers that I'm actually solving the problem that they...
By the way, right, you're not necessarily just proving it to them. You're also trying to assess for yourself whether you've solved the right problem, right? Like,
Exactly.
and you want them to be able to tell you when you're wrong, right? When you didn't include a constraint that's actually, right, that's incredibly important for them.
Right.
Yeah, exactly. And then once you kind of do all of that, the last phase is like often kind of deployment. So getting it into the systems that these mining engineers are actually going to be able to use. So that's kind of the very high level workflow that we found.
So I had asked about iteration, and I realized just in the way that you guys presented the stages that step where you put the model's results in front of the domain experts, inevitably, it seems that there's something they've left out or misrepresented. From my experience, is that what you found in the interviews as well?
Yeah, 100%. I mean, one of my favorite quotes from the paper is we had one practitioner saying that like 99% of the time they have to iterate this through this process, and it feels like almost like a flywheel because like you're constantly proposing solutions, and then there's this like importing constraint I never mentioned before, and that's causing considerations. Or you go to deploy something, you're like, well, our systems can only handle this level of time granularity, so you have to review, revise the model. So this whole project, even though I kind of presented it as this like linear workflow, pretty much every aspect of this is iteration. Like, even at the data processing phase, you realize you don't have the right data for something, you need to, that's going to impact the model. You ask more questions for these domain experts, that's going to impact the model. You go to implement something and you realize it takes hours to solve in this original myth formulation, that's going to impact the model. So pretty much every aspect of this process is iterative.
Yeah, I like that because it seems like showing the results is actually like back to problem elicitation, just trying to figure out what the problem is. And I've kind of found in practice, like some things are just so obvious to like the, mining people or something that they wouldn't even think to tell you this. And they don't even realize that they know this constraint. And then, so this is a kind of a fun process. It makes it iterative. Sorry, Madeleine, you were going to say something.
And I think there's also really important implications, both for the way that we do research and we do teaching in OR, right? Like, if we're concentrating on, parts of the pipeline that are actually really, really well done, and there are the other parts of the pipeline that are really taking the majority of the time, then that's an opportunity for us both as teachers and as researchers. And so what we're finding is that a lot of the slowness of implementing OR solutions, and a lot of the reasons that people don't implement OR solutions, is that the iterations just take too much time because you're going back and forth between people of different expertise, and finding time on the calendar every iteration takes weeks, and so the whole process gets massively delayed. And it's not because of the time required to solve each particular part of it, it's because of the time to go through this flywheel over and over again.
Interesting. What's your theory on why ML is so much easier? Like, as a data person from the OR background, I saw ML, I'm like, oh, this is easy, it's just like OR, and it's just not. And I've seen it in practitioners, and you called it out. Like, what's your theory for why ML is so much faster and so much more broadly used than OR?
Yeah, I mean, I think it's probably the $1 million question for our field these days, right? I think there's kind of two elements. One is that like optimization, it's inherently a bit more bespoke for your application than machine learning, right? Like if I think like an intro to ML course that I used to teach at Cornell, right? It's like, okay, you have a new problem. This is a classification. Here's your scikit-learn package, inputs, outputs, run it through your favorite models and see which one's the best. Whereas OR, like each problem is going to have its own different kinds of constraints. And while there's like definitely templates, right? Like a lot of us solve BRP problems in different flavors, adding those kind of bespoke elements makes it inherently, I guess, a little bit tougher than some of these ML tasks. I also think, please.
I'd go farther and say, look, an ML problem involves a supervised learning problem, right? Involves specifying, the input and the output, right? And then you want to minimize that. That's just the objective. Optimization also can have arbitrarily many constraints, right? So each one of these is a function, and so we can have many, many, many more functions. In ML, they only have one function.
Let me give you a theory that popped when I was reading your paper. And I'll borrow this from Warren Powell. He said this, and I use it a bit. When we do an optimization model, we're actually defining the physics of the problem, and then we're trying to fit the data into that. And then with machine learning or supervised learning, we don't have to tell about the physics of the world. The world is just the data, and if you either like the results or not, but there's nothing else you can do. Like that's the data that you have, and maybe that's some of the difficulty is just figuring out what are the physics of the problem I'm trying to solve.
That's right.
I don't know. Does that sound reasonable? Is that a
Yeah, so it's funny, Mike, when you said you had a theory, you beat me to it. I was about to say I have a theory as well, and it extends on that. And that is that with the ML model, we observe the results. With the optimization model, there's some action that's got to be taken as a consequence of that. And that has got kind of barriers around trust because people are responsible for those outcomes.
Mm-hmm.
At another level and often in the mining example. By the way, Connor, being from the Iron Range of Minnesota, I loved your mining example, your iron ore example.
Yeah.
In that context, people have the physical things that have to happen as a result of what the optimization said that people are on the hook for. So I guess, Mike, I've just kind of piled on your theory.
I'm just going to throw one other kind of theory that I think is important, especially in the context of like talking about HCI, is I think the ML community has also done a much better job making these tools more accessible, right? And like, there's tons of really amazing HCI researchers that have spent the past decade trying to make, editing models, visualizing models, explaining models like super, super easy and kind of intuitive. And I think much to the detriment of our field, we haven't really had the same kind of attention in OR. So even though there's some like inherent like difficulties that make this challenging than ML, we also haven't done a good job kind of building the support structure to make even those like gnarlier tools as accessible as possible.
So you guys mentioned visualization quite a bit in the paper. Could you speak a little bit about the importance of visualization at the different steps?
Yeah, I mean, I think visualization, right, is this like mechanism to kind of gut check whether the outputs of these models even make sense, right? Like, even though in optimization we have this like very technical artifact of like, a MIP model, an LP, an MDP that we've like formulated, because like that artifact is represented in math, it's actually really hard for, even an expert to just look at that and be able to ascertain whether or not it's the right model or it's like missing anything. So we found that in pretty much every project that we interviewed, like the best way people were able to validate these things was just to look at sample output. So if you're building a course schedule, you show all the courses to a bunch of faculty members and see where they start breathing complaints. If you're in that mining example, you show that throughput. And then once you can kind of like situate the outputs of these models in the context in which they're going to be applied, when you're looking at those actual decisions, it becomes a lot easier to kind of highlight these shortcomings.
The domain experts are used to looking at sort of examples of designs or examples of decisions in their domain, and they're not used to looking at complete specifications of optimization problems.
Okay. So it's a little bit of what people are used to seeing. Like a scheduler always looks at a Gantt chart. That's all they ever see.
Yeah, if they had good pattern recognition for the domain, then they can tell you what's wrong. But they don't have good pattern recognition for the domain of optimization problems. This is also related to this question of like, why is ML, why is ML easier to use? I would say that optimization, right, like using it to solve decision problems is almost always in the regime that ML would call distribution shift, right? So if you're solving an ML problem, right, you're just trying to, figure out like in this state of the world, if I leave everything the way it is, what's likely to happen, right? This input-output map right here, right? But in optimization, you're changing something about the way you control the whole system, and it's going to shift all of the dynamics, right? So you would not only know what's going on sort of right in your current operating regime, but even as you change the parameters, what's going to happen in those regimes, which is exactly about modeling the physics of your system.
Yeah, I think in your paper, I liked it. You mentioned in maybe the data section, you were talking about both. I don't know if it was directly, but you were talking about maybe like missing data, or look, when you run an optimization, you're trying to do things you haven't done before. And by definition, you don't have data for that thing you haven't done before. And so you need to collect that data, or you're doing optimization around some piece of data that there's some uncertainty about. And, that's like an output of the machine learning model, maybe the uncertainty around this, but it's an input into this model that's just hard to get your head around. So I think that's another sort of different thing that makes these models more difficult. It's just getting that data. Do you actually trust that this is going to be the new rate if you've never shipped that lane before?
If I change my actions, then how will my suppliers respond? How will my customers respond? How will the iron under the earth, right? Will I find a new vein of iron there, or will I not find a new vein of iron there, right?
Right.
So it felt like in my preliminary conversation with you two, one or both of you had just mentioned that you kind of went into this thinking that the math was going to be the bottleneck, and that wasn't none of the subjects sort of identified that as the bottleneck. What did they flag? What were some consistent patterns around where the problems lived? Madeleine, I think you earlier mentioned the cycle time and the iteration time. What other things popped up?
Yeah, I mean, I think for me, the thing that really stood out is like how much this like human element was this massive bottleneck in the process. Um, to give some context, one of the things we had been working on here at Stanford were these automated modeling tools. So when we went into the interviews, we were expecting people to be talking about like, oh, this is how I look at the literature. These are how I test different assumptions, and like really go like the meat of the interview was going to be about these modeling techniques. And pretty much everyone just spent the time talking about how either frustrating or long or tedious it was to talk with these different domain experts, and how it prompted all these iterations, or how waiting for data from another team took too long, or talking to the deployment people. Like anytime there was this interface between this optimization modeler and like another kind of aspect of the starter ecosystem, it really slowed down the entire process.
Well, this is music to my ears since I'm writing a book on the topic of the humans involved. I did not know that you were going to say that, but you brought a huge smile to my face.
Yeah, and this goes back to our motivation for the project, which was, I'm in this to help people make better decisions. I'd like to reduce inefficiency and waste, and so that's part of what drew me into OR and into sort of better automated decision making. It's what drives a lot of my research in in sort of mathematical optimization, and then also in optimization modeling. So we just completed this paper. On being able to automatically translate from natural language descriptions of optimization problems to outputs. And you say, okay, well, now that we can translate from natural language descriptions of problems to code to solve the problem, and then we can we can pass that to a solver, and we have really good solvers. That's all automated. Okay, what's left? Right? Have we actually attacked the important parts of the things that are really making sort of a bottleneck between that are preventing the use of optimization and or techniques in practice? Our, our research in Magical Box says no, there's still
Right.
a lot to do, and it's not where most of our researchers are concentrating their efforts.
So Madeleine, so what you said in the paper, and that in the paper struck me because I've been thinking about this because I just finished a capstone course, and what I've loved about the capstone course is how much the students had to basically struggle the whole 10 weeks to like solve the problem. And I contrasted that with like a case study. No matter how complicated a case study I write, I mean, I can just throw that into ChatGPT and it like gives me the model and the answer and the whole thing. And we got to teach differently, right?
It's such a challenge in teaching. I mean, I don't know how to adequately simulate for students the complexity of the real world so that they can grapple with it and
Right.
understand, and so that I can even how do I even approach teaching them about these complex challenges? Do I do I know tools to teach them? I mean, for me myself to test out strategies and then assess whether the strategy is working. I just don't have enough time to collect all the experience to do this. But this is something that's driving my research interest now, is understanding better ways of simulating world models, or simulating realistic users, simulating realistic business cases. So they're not just one cut and dried description, like one PDF, right? But
Okay,
they're like
right.
an interactive system that your optimization modeling interactive system can query, right? And then you can start getting at these questions about what's the right approach to querying the real world in order to help
Right.
solve business problems.
So I'd love to push on that a little bit with both of you with this question, which is, what did you learn from this paper that is going to impact the way you teach in the future?
I mean, I'm leaving academia, so maybe I'll defer the teaching to
Oh,
Madeleine.
Connor's totally off the hook.
Yeah.
We'll get you back, Connor. Can't hide.
Yeah, I think I mean, this is for me, this is a major shift for my teaching. Is historically, I guess I've mostly been more of a teaching mathematical optimization, convex optimization, statistics style classes, data science style classes, and now I'm trying to broaden my portfolio. Now, especially now that AI is making it much easier to solve any cut and dried problem, any problem that you can fully specify and solve on your computer. Right? Like any problem that can be solved in the form of just text input and text output, I think is really it's toast. It's easy at this point, right? So the problems that remain are the problems that involve messy interactions with the real world. And so I'm trying to broaden my teaching portfolio to help people understand how to evaluate their solutions and how to improve on their solutions by interacting with either the real world or simulations of the real world.
Yeah, it's interesting as you were talking about that, Madeleine. I was thinking about this new book called The Decision Factory by Adam DeJans Jr. and John Brandon Elam, who but both have been on the podcast at different times around. It was just helpful for me to rethink the idea of optimization as a standalone problem, and more commonly, particularly in real time and near real time systems, as a component in a broader system, and that the elements of uncertainty were such a kind of thing that we tended to marginalize as modelers in the old days. And now, when we're embedded in systems where there's new information coming in all the time, it's potentially impactful. Did the question of uncertainty come up in any of the interviews, and how they were dealing with issues of uncertainty in the data?
Yeah, definitely. I mean, I think there's kind of, this is going to be an overly broad characterization, right? There's like two big buckets of like uncertainty. One is just like in these new problems where there's just no data available, like how do you kind of handle that? And especially when it's like data that's so intrinsic to the problem itself. So for instance, one of our interviewees was working on this like vaccine distribution problem in Africa, and there's like a very, very data scarce environment, right? But so many of those like parameters are kind of necessary to inform policymakers. And I think what's kind of interesting about optimization versus ML in this context, right, is that they were able to read a bunch of literature, kind of guess parameters, right? Because it's like these small scale, you don't need like hundreds of thousands of examples. And then the other thing is in this like kind of polar opposite world where you have tons and tons of data, and like how do you integrate that in kind of like a meaningful way, right? So if you're like, operating some sort of, Amazon style logistics company and you have tons of customer data, right? There's almost too much, right? You can't solve a myth model with hundreds of millions of data. So how do you kind of summarize that uncertainty in a way that's kind of both tractable to the model, but still going to be kind of faithful or like practically useful for this downstream decision making task? And I think there's a lot of like obviously like super interesting research questions on that interface as well.
So I'll have a surprise. It's a minor little point in the paper, but I was kind of surprised that it came up. So there was a point in the paper where you talked about, it was in the model development part, and it seemed like some of the model developers were, I don't know, complaining or talking about like just working with Gurobi and working with CPLEX and adjusting the parameters. I wasn't expecting that. I was expecting that once people formulated a model, they would just feed it into Gurobi solver and be done. But it seemed like there was some other friction there that I wasn't expecting. Can you talk a little bit about that?
I mean, I would say that this is a real vindication for optimization research, and I think I wanted to maybe walk back my point about the importance of human factors. Like there is a role for expertise, right? And the fact that like these are still challenges, right? That it's not like we've completely solved all large scale mixed integer linear programming problems. It's very easy to write down a problem that's too large to solve or too large to solve in the time budget available, right? And so even if it's not the majority of the time that the model developers are spending, it's still, it's still an important part of the process to work on. So there is a lot of room there. And there are a lot of problems that people aren't even bothering to solve because they know they can't actually numerically get to a good enough solution using existing tools. Right. So,
so Madeleine, that kind of brings me up to a teaching point. It's like, we should probably give our students just absurdly large problems and say, solve this. And just to test those skills and sort of work on.
Well, remember that there's a lot of different levels of teaching, and there is still a reason to give them sort of small, cute problems that they can learn from, right? Like you don't have to have every problem be full size industrial. Like we think like I believe that an optimal curriculum builds up the student, and you don't want to jump immediately into the kinds of problems we do without teaching the student like multiplication tables in elementary school, right?
Right.
So
it's tricky.
The role for the simple examples that we currently teach in, intro linear programming classes. Right. But we just want to make sure that before the student graduates, we get them to the real big thing. We give them tools that make sure that they don't just sort of give up when they're when the existing tools that they've learned for these simple problems are inadequate, right? That they have tools that allow them to generalize and approximate, right? And there's something reasonable, even if they can't get the exact optimal.
Which you actually, Madeleine, your timing could not have been better with that last comment. I saw that some of your subjects had talked about how optimality was way less important than coming up with a good solution quickly. And can you guys say a little bit more about some of the things you heard along those lines? Because that's almost blasphemy for those of us that have come up worshiping the term optimal to hear that it's not that important to us.
Yeah, I mean, I think one thing that was like super interesting kind of in that vein, right, is this idea that, all these models are approximations of what these people are trying to solve either, right? So like when we talk about getting like 2% more optimal on a problem that's already an approximation of what the real world phenomena is that we've like constructed, like that is less practically important than just getting, meeting these time constraints or getting something that's going to be easier to explain to clients. Or like actually like implement into these systems, right? Like one kind of interesting example is we talked to one person in the defense sector, and they, because of like contracts and all that, are not allowed to use like any commercial solvers. So like Gurobi, CPLEX, FICO, all of those like amazing things, right? So for him, the person we talked to, right, it was way less about like, can we get an optimal solution? Can we use like these MIP solvers? It was like, I don't want to write a MIP solver from scratch. The MIP solver we have has like 3 different cutting plane families. It's not very effective. Like, I just need something that's going to run in under 5 minutes so that I can ship it and move on with my life. And I think exactly back to your point, like that's such a different kind of pragmatic paradigm than what we're used to, I guess, in like the academic community.
Yeah, but I'll also say, when you go into a consulting project, like one of the first things I always ask is, what's your baseline? What are you doing right now? Right? Because I don't need to get to optimality. I only need to get better than what they're doing right now in order to, make the project worthwhile. Reminds me of the joke about the two people are hiking, they're camping in the forest. A bear finds them, right? And they're running away from the bear. And one says to the other, like, wait, why are we even running? Like, we're not going to outrun the bear. And the other guy's like, I don't need to outrun the bear. I just need to outrun you.
Right.
That's a classic.
Importance of baseline right there. Yeah.
So there was a super interesting innovation I saw from one of your respondents about what he called he or she called the data validator mechanism, but putting guardrails in that flag when input data is in violation of some of the assumptions. Were there other kind of innovations that's jumped out at you that practitioners had come up with that we'd never even thought of?
Yeah, I mean, I think a lot of kind of the support structures and to like get it, like sanity checking optimization models were really interesting to me. So like the data validator was definitely one of those. But one of kind of the more successful artifacts too was also kind of like constraint validators too on the other end. So we think that like we've encoded these constraints in the model. If our solver is working, they're gonna adhere to them. But oftentimes, just like when we're implementing, just like we'd have software bugs in any sort of application, right? Sometimes things are encoded properly. So we had one participant who had like a separate software engineering kind of team essentially take the outputs and write their own unit checks just that they, in natural language, kind of satisfied the constraints that they thought. And that seems to be like a really useful tool, not only to, catch these implementation bugs, but also kind of resolve these like modeling abstraction differences, right? Like maybe how we've been putting that constraint actually doesn't work in this like one edge case. And that's a very practically important edge case. And you only catch that by doing this kind of like third party sanity check.
It's cool. We actually have a guest coming on later this year who's got a startup company that's looking to fundamentally create a different representation of the data to drive large-scale optimization. To Madeleine's point about problems they're too big for us to solve, they've identified this as a bottleneck, the representation itself, and think they've come up with a pretty clever innovation around that. We'll see if it survives the grilling from Mike and I.
Yeah, we're
dig into it.
So I've got my next question is kind of about, it's a thing I've seen with younger engineers, maybe even older ones too. Like your papers seem to focus on almost custom optimization for a particular problem. And I think, one thing we try to teach and I think important about building these models is to separate the data from the model. And I know the experienced people do this, but it's less experienced people tend to tie them together. And your paper sort of does kind of tie them together where you think about the problem, the data, and then the model. Were there any tips that came out of that where people were talking about like, how do you really separate it? How do you separate these things out? How do you build a model that's going to solve the problem that you described? And then I worry about can I get the data to fill it? And if I'm missing some data, I come back. Was there any discussion like that in the interviews or that came out?
So I think there were like kind of two approaches. So, this in our pipeline, we tried to identify like data processing as being distinct from model development because there were some people that really did treat those as like two separate pipelines. And that kind of came up in two ways. One is that like when folks were implementing the model, oftentimes they were waiting on data from other sources, right? So either that data didn't exist, they needed to like talk to doctors in Sierra Leone to figure out like what the parameters were they needed for the model, or there's some data engineering team, but this is priority 10 on their list. So you're just twiddling your thumbs for weeks while you're waiting. So that kind of like level of separation, I think was important in that, when you abstract away what the data is, you can fill in synthetic data to like at least work through your modeling process. But there were some people that kind of like enmeshed them together. But I mean, going back to your point, it seemed like the more successful ones, so the ones that like usually led to deployments, tended to kind of abstract them away and do kind of the validation separately and think of it as more like a pipeline.
Yeah, so the synthetic data is a good idea, right? You sort of, this is the data we think we're going to get. We don't know if we're going to get it or not, but let's just pretend like we have it. I can build the model and then I can work on getting that data. And if I don't get the data, it's an iterative process anyway. I go back and I tweak the model. Perfect.
So I saw that one of your respondents sort of said, hey, somebody could be using this model, coming up with wrong answers and not even know it. How, from your experience with this research and more broadly the work that you two have been doing, are there tips and tricks around how do we prevent that from happening?
Yeah, I mean, I think this is why kind of this intersection of HCI and OR is like so important. I mean, there's been like really, really fantastic work from researchers like, Jess Workman-Vaughan, Jessica Hallman, who like from the ML world, who also have this kind of like HCI connection on like, how do we debug these models? How do we, check these edge cases? And I think this is like really key to our field, right? Like even for expert users right now, like how do people debug the models? Like, I did my PhD in integer programming. I've definitely wrote a lot of models that had issues that like I only caught weeks later than I should. And the reason why is like the only way that we sanity check them is you look at some outputs, you kind of like do a sniff test and you hope that you're right? But, these are the kind of problems like patching insidious errors, getting people to attend to the right parts of things. That's like HCI as a field, like bread and butter, right? So if we can get more HCI researchers excited about these questions and like, how do we do this, validation in kind of a human friendly way, I think it's going to, enable not just like these LLM powered systems to be more accurate, but also, current workflows, right?
Speaking of that, like, you did at the end of your paper, like one of the things about implementation was good documentation. I think documentation is like super hard, and it feels to me like what I've seen is if I can build the documentation actually into the application, it's much better. It's like used to be tooltips, and maybe now it's LLM help. But was there anything that came up with that as like really thinking hard about the ease of use, so you don't have to have some document that no one's going to read anyway on how to use this? Like,
okay, the documentation used to be super hard. Now,
Yes.
Okay.
Now
So,
you just have to ask for it, and it's done.
yeah, you have to ask for it. It's okay. Maybe the hard part is now getting your users to read the documentation.
Well, yeah. And I agree with you that building it into the tools, so that it's obvious is the right way to go, and that is, I think, probably still at least a little bit hard.
Okay. Yeah.
But Connor, do you want to say more about?
Yeah, I mean, it's kind of tangential, right? I feel like that this idea of how do we like enable users to kind of like navigate these tools has been like a really exciting research area too. So like Cam Lee's group at Purdue has like a few like really amazing papers on like using LLMs as kind of a way to like ask counterfactuals on kind of trained optimization models. And you can imagine kind of like a production analog of that, right? Like you're an OR expert handing off a model to the deployment team. It used to be that deployment teams had to come back to you for every question about this model. Like, what are the data validation? How do we like integrate this into our systems? What's the runtime? What's Gurobi? How do we call Gurobi? And it's like now you can use LLMs as this like communication intermediary. Hopefully it'll just make these things better.
Well, that organically brings us, Connor, to the next phase of your career. Tell us about Percepta and kind of what you anticipate doing there at this intersection of LLMs and optimization and modeling.
Yeah, so I'm going to give like one giant disclaimer that I have not started at Percepta. So the tool will, if you're hearing this and like I'm doing a bad job characterizing the work, don't hold me accountable. But
this is your forecasted work, Connor, not your actual, your forecast.
Forecast, yeah, and hopefully I'll do good enough forecasting that I'll still have the job in a couple months when I start. But I think what Percepta's really been focused on is like kind of this like last mile of analytics, right? Which is, we have all these amazing LM tools, we have all these amazing OR tools, but they're not being used. Right. So how can we like enable these companies to actually, use these tools in a kind of a transformational way, right? Like if you had an OR expert able to redesign how we like run hospital operations, what would that look like? And how do we make sure that those systems can actually be adopted by the users? So Percepta has been kind of taking like an LM forward approach towards that. So they've been working with a lot of their clients on kind of these hybrid OR LLM systems as a way to kind of improve adoption and like better decision making in these like critical industries like healthcare and power grid. So I'm selfishly super excited because I spent the last like 2+ years of my life thinking about how we can make optimization more accessible. And, inherently my research is like motivated by like these implementation gaps, but it's really hard to do that in academia because I'm not the one implementing it. So I think that's really exciting about Percepta is being able to actually look at that last mile and see kind of what that implementation is done and see how we can, design research questions and better tools to, improve these adoption.
Excellent. So last question for you, Madeleine, and that is in our previous conversation, you sort of questioned how much did you personally or the OR community broadly have to contribute to these problems that we've been talking about really for the last 30+ minutes? And my question is, if not us, then who?
Yeah, I think this is a really big question in the context of the current wave of AI. I think there's sort of two forces that are countervailing. One is I believe in the importance of expertise, right? And that you get deeper and deeper into like a sort of a modular breaking up of really hard, challenging problems, right? If you can break it up into modules, and then you can get experts to get super, super deep and really, really understand their individual module, they can improve their module. And then when you string the modules all together, then you get something great. Right? This is a sort of traditional engineering approach to problem solving, right? And it's really, really effective as long as you can get the modules right? Now with AI, I think there's a major change in which of those modules are easy and which of those modules are hard. And some modules that used to be hard are now easy. Right? We talked about documentation, and I also think that it's coming for like optimization more generally, because optimization is right. You can see how good the objective is, and that makes it a really easy target for recursive self-improvement. And I expect to see major innovations in optimization software largely coming from sort of pure AI-driven approaches. Rather than from human-driven approaches, right? Now, you still need some experts to supervise or even tell the AI that that's the problem to solve. But maybe you need fewer, or the kind of work is just going to change. Now, I think that's still important. That's important work. Then we've also sort of highlighted in this paper that a lot of the things that are really slowing down OR in practice are the human implementation challenges. That's also important work, and there are people who study that. For example, organization behavior people, right, study the challenges of working across teams. We have many people with that expertise in management science and engineering here at Stanford. Yes. Right. So, I'm a my training is a mathematical optimizer. My training is really mathematical. And I care about solving these big challenging problems. So I want to make sure they're going to get solved. right? I want to understand which parts are being solved well and which parts are being solved poorly right now. But just because I identified this part, needs work on it, doesn't mean that I have to work on all the parts that I identify that need work on them, right? I think it's also important to play to your expertise, right? And build on the skills that you've already built. So my claim is that I do not have substantial existing expertise in HCI or in organizational behavior, and that those are some of the skills that are needed to resolve some of these problems. Now, collaborations between people with differing expertise, right, can really be very powerful at dealing with maybe like the organizational behavior people haven't been looking at OR workflows, right? And so you can find a collaboration there and you can really make progress, right? But I mean, I guess what I'm saying is I also believe in the expertise that they've built, and I don't want to try to go in and say, I'm so brilliant, I'm going to redesign it, right? I want to work with what's already known.
Yeah, I just as a comment, and then I'm going to throw it over to Mike to close, and that is, I think the MS&E department is a great opportunity simply because of the diversity of expertise that we have there. When I was a student in my dissertation, one of the things I'm most proud of is that I brought two faculty that had been in the same department for 25 years, had never been on the same committee together, by seeing how their problems connected. And so my hope is that that's a tradition that'll continue in the department.
Yeah, no, that's wonderful. Yeah, that's part of what I love about being an MS&E in such a diverse department. But I would say, who's going to work at the intersection? Who's going to work, sort of between these disciplines? And it's the students, right? The students are always right there. They're the answer, right? To how to break these silos.
Perfect. I think that's a great way to wrap up. We'll put a link to your paper in the show notes. I appreciate Madeleine your time, Connor your time. So thanks for joining us on the podcast.
Wonderful. Thank you.
Thanks so much for having us.